mixed bag, climatology and geomorphology. Once more, because this is where we find most challenges. All right. They say refer to figure 2.1 showing a high pressure and a low pressure cell in the southern hemisphere. Match the statements below with the high pressure cell or the low pressure cell. Write down your answer next to the question numbers 2.11 to 2.1.8 in the answer book. All right. 2.1.1 says, sorry, let us first look at the figure. Sorry about that. Let's look at the figure. So this is, let us refer to this one. Go to figure A, which is a high pressure cell. Figure B, a low pressure cell. All right. So they say associated with rising A. Is it going to be a high pressure cell or a low pressure cell? And for this case, that would be a low pressure cell. It is the one that is associated with rising A. Let's try to illustrate it here on our blank page. Okay. Because we know that in low pressure cells, air converges, then it's going to rise. This is low pressure cells. All right. So which makes our option for 2.1.1 to be a low pressure cell. 2.1.2 says air diverges on the surface from this pressure cell. Air diverges. So we go back and we show air diverges on the surface. Okay. Now let us try to demonstrate here a high pressure cell first. In high pressure cell, air subsides or descends. After descending, then it's going to diverge. Because to diverge when air moves away. Okay. So air subsides, then diverges. This is the surface. Because in high pressure cells in the upper atmosphere, air converges. You see, it is converging here, and after converging, it is able to subside, or it is able to descend, forming a high pressure cell. Then eventually it diverges out on the surface. So which means if we go back to our options, 2.1.2, it will be a high pressure. 2.1.3, associated with clockwise movement of A. Don't forget they said these pressure cells are situated in the southern hemisphere. All right. So which one between the low pressure cell and the high pressure cells move in a clockwise direction? Go back to our blank page to try to illustrate. If we have this globe here, which shows northern hemisphere and the southern hemisphere. So we know that in the northern hemisphere, low pressure cells, so in the southern hemisphere, low pressure cells rotates in a clockwise direction, and they rotate anti-clockwise in the northern hemisphere. This is typical of low pressure cells. And then high pressure cells, they rotate clockwise. These are high pressure cells. They rotate clockwise in the southern hemisphere and anti-clockwise in the southern hemisphere. So these are high pressure cells. But our question is saying associated with clockwise movement of air in the southern hemisphere. clockwise movement in the southern hemisphere, which is this one here. This clockwise movement in the southern hemisphere, which is typical of a low pressure cell. 2.1.4, unstable weather conditions over the interior. So remember, when they say unstable weather conditions, so they are referring to things, for example, rainfall, winds, overcast condition, etc. Right. We can as well talk about, let's say, thunderstorms. So all these are examples of unstable conditions. Now, how do these develop? We try to illustrate on our blank page. We know that rainfall develops as a result of air ascending. When air ascends, it condenses, forming clouds and as well rainfall, accompanied by thunderstorms. Right? So, does air rise in low pressure cells or in high pressure cells? And we did indicate up here that in low pressure cells, air rises. See, when it rises, there will be formation of overcast clouds and there will be rainfall. So, which means that unstable conditions are associated in low pressure cells. In the low pressure cells. 2.15 associated with ridging. What is ridging? This refers to the elongation or extension of isobars away from a high pressure. So the moment I say high pressure, definitely you know what our answer is, right? Because it says associated with ridging. So ridging is common in high pressure. So what they mean? Something like this is happening. You see isobars extending away. You see, so it means this is elongation. So this part here, you can see what refer to as ridging. Isobars are extending, you see, towards that other point. So that is ridging, which is common of high pressure cells. So we say high pressure. Okay. Associated with heavy rainfall and hail, this will of course be a low pressure, because we say that in low pressure cells, we say that air rises. When it rises, it condenses, forming cloud that is accompanied by heavy rainfalls. That's why we say that to be a low pressure. 2.1.7 dominates the land in winter. That will be a high pressure cell. In the winter, the high pressure cell dominates the land. How do we show that? If we illustrate it down here regarding a high pressure cell, this could be the map of South Africa, and normally they're going to show something of that sort or that nature, indicating a high pressure. When this happens, now this shows a high pressure cell dominating the land or the interior in winter. If it was summer, it was going to be like this, because in summer, a low pressure cell dominates the land. So this is winter, and this is summer. Okay. So big wind conditions develop when it interacts with a coastal low. That would be a high pressure. A high pressure cell. So if I can as well illustrate that on a diagram, it's going to be, because they say big wind conditions develop when it interacts with a coastal low. Okay. So it means if this is our high pressure cell, for example, it means we're going to have our coastal, in here we see L, meaning a coastal low here. So if we have a high pressure cell, now there will be a pressure gradient, indicating now winds are moving from a high pressure to the low pressure, and these winds are referred to as the big winds. Right. So they develop between the interaction of a high pressure cell over the land and the coastal over the coast. All right. So that is for question 2.1. 2.1. Okay. Question 2.2. They say choose a concept from column B that matches this description in column A. Area drained by a river and its tributaries. That will be a drainage basin. For number D, number 2.2.2, a high-lying area that separates two different drainage basins. That will be a watershed, which is F. 2.2.3, starting point of a river. That will be the source, which is G. 2.4, term that describes the main river and its tributaries. That will be E, which is the river system. Point where the river enters the sea, that will be the river mouth, which is H. Elevated land that separates streams in the same drainage basin, that will be an interflow, which is B. Point along the river where two or more streams meet, that will be C, which is the confluence. Okay. 2.3 figure shows the path of a tropical cyclone. So give a path of a tropical cyclone. So they're saying give evidence that this tropical cyclone is in the southern hemisphere. How do we tell it is in the southern hemisphere? Firstly, can we indicate the clockwise rotation, clockwise symbol, and as well countries found in the southern hemisphere. Countries found in the southern hemisphere. In the southern hemisphere. What else can we look at? The date, which is April. So I think it is still summer. April. Yeah, I think that date about the date. Which shows summer. Which shows summer in southern hemisphere, because April is still not yet winter. We're still experiencing high temperatures. What else can we look at? The Mozambique Channel, which is in the southern hemisphere, as well mentioned. The Mozambique Channel found in the southern hemisphere. All right. Now they say 2.3.2. Why is the Mozambique Channel usually ideal for the increase in temperature within the tropical cyclone? So consider Mozambique Channel experiences warm ocean currents which rises the ocean temperatures. Experiences warm ocean currents which rises ocean temperatures. 2.3.3, explain how the intensity of the tropical cyclone increased as it moved from area A to area B. Area A, area. So explain how the intensity of the tropical cyclone increased as it moved from area A to area B. So you can see area A to area B. This is the Mozambique channel. So don't have to explain how the intensity of the cyclone increased. Okay. So that is what, which question is that? That is question 2.3.3. Question 2.3.3. So the intensity increased massively the warm temperatures resulted into high rate of evaporation there was high rate of condensation which resulted into high latent heat supply. As well said, there was less friction with the land to slow down the winds and intensity of the cyclone. As well said, and this area due to high temperatures it resulted in further development of a low pressure. So that's how the intensity of the cyclone increased as it moved from area A to area B. All right. 2.3.4 discuss the conditions that could have caused the cyclone to weaken as it reached area C. So let's remove this one so that you can see clearly. So they say discuss the conditions that could have caused the cyclone to weaken as it reached area. So this is area C here. That's area C is almost close to the land. All right. Let's go back. Discuss the conditions that could have caused the cyclone to weaken as it moved to area C. That is question 2.4. 2.3.4. This is 2.3.4. 2.3. So I could say friction with the land weakened cyclone, as well say cyclone moved into cooler areas, because we know that cyclones, they love warm conditions. So if they move towards cooler areas, this as well weakens them. Okay, as well say less supply, less evaporation, and condensation, meaning less supply of latent heat. So let's check again. At point C would have been the reason which caused the cyclone to weaken. Spoke about friction with the land, the supply of latent heat, moving into cooler areas, among others. So for now, I think we shall go with those factors. Let's proceed to question 2.3.5, which says evaluate the physical negative impact of the coast cyclones along the coast of Mozambique. The physical negative impact of the cyclone along the coast of Mozambique. It is 2.3.5. The negative, so cause coastal flooding, destroying the coastal areas, results into flooding of farms, causing soil erosion, infrastructures, such as roads, buildings, destroys the natural habitats, disrupts the ecosystems. So also, due to heavy rains, it could, cause landslides and landslides. So, among other physical impacts. All right, so that is for question 2.3. So we're going to go to 2.5, which says, refer to figure 2.5, which shows a river capture or stream piracy. Define the concept, river capture, as shown in sketch B. So this is sketch B here. So before, you can see we have a watershed. There's this other stream flowing the other side, the other one flowing this other side. So there's a watershed in between them. So this is after capture. You can see this one was able now to store the other river, and this one was left without the source. Okay, so define the concept river capture, so this is what I say, energetic river stills headwaters of a weak river stills, or can as well say robs. Okay, stills or robs. Identify features 1 and 2 of river capture in sketch B. Features 1 and 2 of river capture. So feature 1, the elbow of capture. Feature 1, that's going to be the elbow of capture. What do you call it? The elbow of capture? As you can see, it forms an elbow. So this is an elbow, so like there is a curving here. So notice the elbow of capture, it is the point where capturing took place. And feature 2, that would be the wind gap. The wind gap or a dry pen. So that is an area. Feature 2, this point here, that area which is now dry. There's no more water at that particular point. Okay. Then we look at question 2.5.3. What could have caused the capture stream to erode through the watershed? Remember, when they say capture stream, this is the same as the energetic stream, or the pirate, or the one which store water. Right. So when they say, what could have caused the capture stream to be able to erode through the watershed? We've said the watershed, like you can see here, this is our watershed. Figure A high-lying area which separates two different rivers or different basins. So you can see that this river was able now to erode backward through this watershed and was able now to intercept the other river. That's why when you look at the other figure B, you can see nicely that the other river has been robbed of its source. Okay, and the question is asking what could have caused the capital stream or the energetic stream or the pirate or the one which stole water to erode through the watershed. 253. So you could say it was flowing over steeper gradient. That's why it was able to erode faster. Steeper gradient able to erode watershed faster. Or as well as say it was flowing over a less resistant rock. To erode faster. Check the question again. What could have made it to cut the capital stream to erode through? As well as say it was more energetic. Making it able to erode through. Okay. 2.5.4 explain the process that resulted in the formation of the Misfit stream. Which one is a Misfit stream? You can see this is our Misfit stream. This is our Misfit stream here. Misfit stream. Now a Misfit stream, that is for question. Misfit stream would say a stream that lost its source. That is a Misfit stream. So we need to explain the process that resulted in the formation of a Misfit stream. That is question 2.54. 2.54. So I could say energetic river erode through the watershed. Energetic river intercept and steals the headwaters of a weak stream. The lower part of the weak stream is left without the source. Forming a misfit. All right, that is for question 2.5.4. So we say an energetic river erode through the watershed, as you can see here. So this is our energetic river. She was able to do Edward erosion through the watershed. Was able now to intercept this stream and eventually stealing its source. That's why here, after capturing, you can see that now this stream no longer has its source. It has been now diverted, or it has been stolen, which means the Misfit no longer has any water supply. That is how we could explain the formation of a Misfit stream. All right. 2.5.5 says, describe the change in the flow characteristics of the captor stream. What will happen to the captor stream? Would say its erosive power will increase, its velocity will increase as well. We're flowing so fast. It will erode vertically, be rejuvenated, to gain more water, to gain more volume of water, etc. All right. So question 2.6 says, figure 2.6 shows a river profile. All right. So 2.6.1 is the river profile in figure 2.6 graded or ungraded. So our answer for this case is going to be ungraded. Give evidence because we could say the profile is not rough or not smooth. Rough or not smooth. As well say it has temporary base levels of erosion, temporary base levels of erosion. It is the waterfalls and rapids. So you can see this profile is not smooth because you can see here there are waterfalls around this other point. You see, so the profile is not smooth throughout. That's why we say it is typical of an ungraded profile. So 2.6.3, why would there be more erosion than deposition at A? Then we could say because the river velocity is high, velocity is high, gradient is steep. Let's go. I think we'll see this on our blank page 263. We said river velocity is high. The gradient is steep. Allowing more erosion. Okay, so that's why we say that at A there will be more erosion than deposition. Look at the gradient. It is too steep. That's why there's a waterfall. Too steep. So where it is too steep, we don't expect materials to be deposited. Instead, the river will be eroding vertically, and as well, due to steep gradient, the velocity or the speed of the river is going to be high. Therefore, it will be eroding instead of depositing materials. 2.64, it says in a paragraph of 8 lines, explain the fluvial processes that a river undergoes to reach a graded profile. As we know, we say that this profile is ungraded as a result of temporary base levels of erosion like waterfalls, the rough surface, etc. So let's see, explain the fluvial processes that a river undergoes to reach a graded profile. So you could say the river erodes away the temporary base levels including rocks, rapids, waterfalls. The eroded materials, are transported downstream. The profile which was rough now it is smooth. This smooth therefore we shall have a new graded profile. Okay. So question 1.3 are based on climatology. The figure 1.3 shows a mid-latitude cyclone on a synoptic weather map of southern Africa. Let's check figure 1.3. Figure 1.3 there. You can see we have, there is the symbol of a cold front and home front. There is a symbol for high pressure source. You can as well look at the isobars and sketch map of southern Africa. All right. So they say, give evidence from the diagram that suggests that the weather system A is a mid-latitude, a cyclone. So what evidence, yes, can we give to suggest that the weather system at A is a mid-latitude cyclone? For this question, we can see it has a cold front and a warm front. And you can say because of the cold front, the symbol for the cold front, the symbol for the warm front as well. Symbol for the warm front as well. Set a bit. Talk about its location, located in the western side. Located the western side. Located in the west. That's where the MLC or the mid-latitude cyclones do originate, among other factors. Why does this weather system originate at the polar front? Then we know at the polar front, that's where we have warm winds, mid, cold winds. Okay. Because the polar front is a region where different air masses meet. That includes warm winds and the cold winds. So the mid-latitude cyclones do develop at the polar front. That is where the cold easterly winds meet with the warm westerly winds. Now give a reason for the direction of movement of this weather system. Now, its direction of movement, we know they move from west to east. But the question is asking that why do they move from west to east? Then we say they are driven by the westerly winds. So if you look at the diagram, usually mid-latitude cyclones, they move from the west going to the east. Reason? Because of the easterly winds. Okay. Then 1.3.4, why is the cold front associated with severe weather conditions? Then we say because it lowers down temperatures. It lowers down temperatures and as well results into overcast conditions and heavy rains. Okay. 135. Explain the formation of the stage of development shown in figure 1.3 of the mid-latitude cyclone. Explain the formation of stage of development in figure 1.3. Let's see the stage of development. I think this is going to be the occlusion stage because we can see the cold front and warm front are mixing up, which is the occlusion stage. Okay, so I'm going to explain 1.3.5 down here. But we said it is an occlusion stage. We say it forms. I said the cold front travels faster than the warm front, Okay. Cold front narrows the warm sector. Eventually, cold front eventually purchase the warm front. So what does that mean? If you look in the mature stage, for example, this could be our cold front. This is the warm front. But you know that the cold front is more dense, so it travels faster, so it keeps on narrowing the gap. Eventually, it will intercept the warm front, creating an occlusion. Right. For question 1.3.6, why does the cold front of the mid-latitude cyclone have a positive impact on agricultural activities in the Western Cape? Then we could say it causes winter rainfall, which favors farming. It allows growth of crops which are suitable for cold conditions. Okay.